Welcome to this presentation 10 of this algebraic structures class and we are using this free online textbook, Abstract Algebra, Theory and Applications by Thomas Judson. So we are just moving to the chapter next to the symmetric groups because in the previous two presentations we discussed the cyclic groups and symmetric groups, two very important classes of subgroups or rather groups. So now let's take up things in general and we will be building up on the examples that we already constructed. Okay, so let's just take in general a group G and a subgroup H of that group G. It could be proper or improper. Okay, so the relation is defined in the following manner. Okay, that is elements A and B of G, they are related if A inverse B belongs to H. Okay, and again, of course, if A and B are in H, then A inverse B, H being a subgroup, will be in H. So all the elements in H are related via this relation. But now we are expanding this to two elements of, or the elements of group in general. So let's check whether this relation is an equivalence relation. That is, the first thing is if it is reflexive. Okay, and reflexive means whether A is related to A, right, for all A in G, right? Okay, so you can see that answer to this is yes, because for any A in G, if you look at this, A inverse A, according to this requirement, I mean, we have A and B both being A, that becomes identity. And since H is a subgroup, therefore, identity is in H. So what we have is, yes, it is reflexive, right? Then the next step to verify was what? Whether it is symmetric. I have no idea why I copied it, but anyways. So symmetric, and symmetric means if I have A related to B, which means what? Which means that A inverse B is in H. All right. Now, what do we need? We need to see or check whether B is related to A. And B is related to A means that we just interchange the places, and this and B inverse A should be in H, and which obviously it would be, because what happens is H is a subgroup, and when we take the inverse of this element, then what will happen is the order of these elements will reverse, right? So, and the inverse is going to be in H, right? Because H is a subgroup, right? So I'm not writing it, but you know that what is giving us this relation is that H is a subgroup of G. And then what happens? As I said, remember, inverse of a product is product of the inverses in the reverse order, if you remember from presentation 2 or 3, wherever it was. Okay, so this is B inverse and then inverse, and then what we have, we simply have, I made a mistake, I apologize, B inverse, and then we have A inverse inverse. Again, there is no rush, so I should not be in rush. Okay, so this is going to be B inverse, and A inverse inverse would be what? Simply A, and that belongs to H, right? And this means what? B is related to A. So answer to symmetric is that yes, it is symmetric, right? Now let's check if it will be transitive. Okay, and what do we need for the transitivity? We need this, that if A is related to B for elements in G, of course, okay, and B is related to C, again, C is an element of G, okay, so B is related to C, then what has to happen? We need that. So first of all, what these mean is that A inverse B and B inverse C will be in H, right? Okay. So what we have to show is that A inverse C will also be in H. And that's that looks like to be true right from here because these two are elements of H and H is a subgroup, right? So since H is a subgroup, okay, of G, all right, what has to happen? It will be closed with respect to multiplication. Now remember, I'm not writing composition anymore. And because of the associativity, I'm not writing brackets anymore either. All right. So what happens? This BB inverse, that will simply become identity. So when that becomes identity, let me write that down, even though by now it should have become quite trivial for you, I hope. Okay. And EC is C. Okay. So this is A inverse C. Okay. And notice this being product of two elements in H has to be in H, right? So A inverse C is in H. So what that means then is that A is related to C, right? So it is like this, that transitivity is also satisfied, okay? Now, let us look at the equivalence classes of an element A in G. So remember this, the equivalence class of A, we may denote it by bracket A, or I think earlier we denoted by a bar over A, either way. So what is it? That consists of X in G, of course, such that A inverse X is in H, okay? So A inverse X belongs to H. So what that means is this, that A is a subset of AH. Now let's see, if we take an element AH in this left coset, A capital H, all right, then, or rather, let's see this here, I'm sorry. If we take an element, say y in AH, then what that means is that y should be what? AH for some H in capital H, right? Taking it like this was not really directly leading us anywhere, but what this shows us is that then what happens? If we multiply by A on the left, okay, then we get A inverse Y equals, sorry, A inverse, yes, Y equals H, okay, and which is in capital H. So what that will mean is that A is related to Y, and I took wrong symbol, okay, and which automatically means Y is related to A, all right, and that will mean that Y is in, okay, that will mean that Y is in, so Y is in equivalence class of A because here Y is related to A, right? And that will mean what? That this left coset of A is a subset of that equivalence class of A, right? So the equivalence class of A is the left coset here. And if you think that we are just repeating ourselves, you shall see that the things that we have done, many of them look like different things, but they will turn out to be the same. And I'm going to do this. That is, I'm going to take up an example which will look very much like what we had just done, just maybe 3, 4 presentations ago. So let us consider G, the group, as the group of integers with respect to addition of integers, and its subgroup as the subgroup consisting of multiples of 5, okay, which is a cyclic group generated by the element 5. Now, if you look at its uh, cosets or left cosets, you may notice that if we write this, what we have is that we simply get 0 plus 5n, okay, which is again going to be back to simply 5n or multiples of 5. Now, if you look at the left cosets of 1 in this manner, then what do you get? You simply get 1 plus 5n. Now, remember what 1 plus 5n is? This is, if you start changing the values of n, this will give you all the integers that are related to 1 modulo 5, right? So this is just the equivalence class of 1. And remember, with respect to plus modulo 5, right? And likewise, the other ones behave the same. That is, if we look at the equivalence class of 2, then again this is 2 plus 5n. So these are all the elements that are related to 2 modulo 5. So this is the equivalence class of 2 over there, right? And in the same manner, the equivalence classes of 3 and 4 are the sets of integers that are related to 3 and 4 modulo 5 respectively. So what we have is that the left cosets, okay, of this subgroup 5, okay, of Z are simply the integers modulo 5, right? Okay. Yeah, so yeah, they which are again the left cosets of this subgroup of multiples of 5 are these equivalence classes, modulo 5 for 0, 1, 2, 3, 4, and then they repeat. Now, let's take another example. And for this example, let's move on to the group of complex numbers with multiplication. I'm just introducing some groups to you that I did not introduce before. So the binary operation here is complex multiplication, okay? And what I meant by C star is that C star is simply, or let me take the proper C star here. So again, C star is the set of complex numbers, okay, minus the element 0, okay, because 0 does not have multiplicative inverse. So, and our operation is complex multiplication. Now, notice this, that if we take H to be the subset. We considered this subset a little while ago. Okay, let me just call it I may call it theta, and where theta is a real number. Okay, so theta belongs to the set of real numbers. Now to prove that this H is a subgroup of C star, since we know that C star is a group with respect to multiplication, all we need to show is that if I take elements E theta, let me call another element, say E phi, right? So then what we have to show is that if these belong to H, then we have to show that the AB inverse, that is this element times the inverse of this element, is also in H. Remember that now we don't have to prove all the properties, just this much is enough. So we got that, and this equals, if we just go by using the power rules, okay, so here this will just become its negative power, right? And remember, theta and phi, they are real numbers, so this simply is e to the power I, and then what we have, theta minus phi. Now theta is a real number, phi is a real number, so theta plus phi will also be, theta plus phi will also, or rather theta minus phi will also be a real number. So this belongs to H. Okay, and remember, by the Euler's formula, we have another representation of this value, that is, we may call it cosine theta plus I sine theta, right? And so where do all these live? Here, if you look at the magnitude of I theta, e to the I theta, okay, that will be the magnitude of cosine theta plus I sine theta, all right, and which equals how much? Just this modulus, okay? So that is, we have a square of cosine. Let's write that down. So we got a square of cosine theta plus a square of sine theta, and that by the Pythagorean identity becomes a 1. And so what happens? Every element here in H has a length of 1. So they will all just be on the unit circle in the complex plane. Okay. So this is our non-zero complex numbers. You can see that we have removed 0 here. And if we take the relation that we had, that say W and R are related, which means that W inverse R belongs to H. Okay, and if I am in H, what happens is that the modulus would be 1. That's what the property of H is, right? Okay, so which will mean 1 over omega, or times modulus of R is 1. So what happens now is that the two will have the same length. So the two elements that are related, or that are in the, say for example, if I look at a coset of R by H, or the coset of R, H by R, I'm sorry, then what will that contain? All values, right, such that the, let's say all values omega, such that the distance of omega from origin is R. So again, what that will be? So that will be the set of all the uh, elements that are at a distance modulus of r from the origin, right? So that will be a circle of radius r. So what the cosets of H will be? They will be circles of radius r, or the points on the circumference of circle of radius r, if we are talking about r, h, right? So let's just write that in our document. So here we can say that the coset ZH consists of the points on the circumference of this circle with center at the origin and radius the modulus of Z, and of course Z is a non-zero element of the set of complex numbers. Okay, and let's now turn to some finite sets or finite groups. Now let us take the quaternion group and a subgroup. Now I'm expressing a subgroup by C, and the subgroup that I'm taking is negative 1, 1, which we had seen is a subgroup of H. So in here, if we look at the left cosets, who they will be, one will be C, and then say we go IC, that will be the same as negative IC. All right, and all that will happen is that's going to be negative I, or if I was taking by uh, I, then it will be I negative I. Okay, so continuing in that manner, what we realize is that the left cosets of this is these four subsets of H. All right, so these are the left cosets of this subset. Taking another group, likewise, say we take Z15, the group of integers modulo 15 with addition modulo 15, and we take this subgroup is generated by 3, as you can see, and has how many? 5 elements. So what will happen is we will expect, like, this is 15, this is 5, so we'll expect 3 different cosets of this, and let's look at them. So we can see the subgroup itself is a coset by any of the elements of the group, and if we add 1 on the left, we get a coset with these 5 elements, right? And then adding 2 will give these 5, and they all just accumulate to the entire Z15, and we have 3 different cosets by a subgroup of 5 elements, and the group has how many? 15 elements, right? Now let us quickly recall our symmetric group S3. Okay, and we are just taking it as the symmetries of an equilateral triangle. So here we didn't make any change. So this is identity, and what happens here is this, that see, this 3 has taken place of 1, 1 has taken place of 2, and 2 has taken place of 3. That's what this indicates. Here 2 has taken place of 1, 3 has that of 2, and 1 that of 3. So that's what is indicated in here. And here what has happened? Just 1 and 2 have just switched their places. In this case, 2 and 3 have switched their places. And here, 1 and 3 switched places. And these are the cyclic permutation notations that we had adopted for them. All right, so instead of doing this by hand, let's just quickly review our Sage Math calculations, or our Sage Math methods in fact. So let's just for practice keep it simple. So we are taking G as symmetric group on 3 symbols, okay? And let's ask it to list G. So we have the three elements that we had. All right. Now what we will do is let's just take an element or select any element. Let's select an element of order 2. For example, this is a transposition, remember? And this has order 2, 1, 2 times 1, 2 will be the identity. So we took that. And then what we are going to do is, and here this is command driven. Okay, I hope once I get better at it, I'll give you better commands. So in here, what I have is that I am just asking it to give me a subgroup H that's generated by this element A that we used. Okay, let us list H, and we already know it has only two elements. Okay, and now what we would like to do is that we would like to get the left cosets. Okay, so now what we are going to do is we are going to ask for the cosets of H in G, and by default it does right cosets. Okay, so we have to tell it that we want the left cosets, and here it gives us the three cosets that will arise because the group has 6 elements, subgroup has 2, so there will be, this is 1 and second, and here we got our third coset, right? Okay, so there are 3 of them. So now let's extend this to a discussion in general. So let G be a finite group, okay? So the group that we have now is, let's assume, so say our group is a finite group, okay? Finite group, okay? And N is the number of elements in the group, okay? Now, and let's assume that this enclosure denotes that set, the underlying set of G, and I'm not, putting dots for the elements. So there are, how many elements are here? There are n elements in here, okay? Now let's let this be a subgroup of this group, okay? So let's call this subgroup H, okay? And our group is the group G, okay? So now what we are going to see is this, that we are going to define the, we are going to look at the equivalence classes that are created by, remember the equivalence relation that we had, that A is related to B when A inverse B is in H. All right. So now what we are going to do is this, that we are going to show that any two cosets in of this subgroup H are in a one-to-one correspondence. In other words, what will happen is now we are in a finite situation. So if they have one-onto correspondence between them, then the number of elements between the two would be the same. Okay, so let's let this be H, and then this be GH, where G is an element of G. All right. So in case G belongs to H, then what will happen? GH will become H. We don't have anything else to prove. Okay. Now say G does not belong to H. Say G is not in H. Still, the correspondence that we are going to show is going to be true. So we have H here, and we have G, actually capital H, we have to be sensitive with that. And a very natural correspondence to define here would be, let's carry an element H in here too, an element GH in here. Okay, and let's call this map F. So what our f is for any little h in capital H, we are taking it to GH in the coset GH. So what we want to show is that this is 1, 1 and onto. So for 1, 1, what we have to show is that if FH1 equals FH2, then H1 and H2 are the same. So what does this mean? If we go by definition, this means GH1 and this means GH2. Now, remember, left cancellation law holds in a group. So that implies that H1 equals H2 and F is 1 to 1. So we showed that. Okay. Now we have to show that this map is onto. That is, for onto, what we have to do is take any y in GH, okay, to find H in H such that FH or FH is Y. All right, now let me just make some space here. So now you know Y is in GH. So what will happen is that Y will be of the form GH, right? Okay, for some element, let's just call it GH1. So have H1 in H such that GH1 is Y. All right. So what happens here is this then, that if you multiply both the sides by G inverse, then H1 will be G inverse Y, right? Now notice this, that if we take f of H1, then that will be, what will that be? That will be GH1. So, or, I'm sorry, I'm all over here. Okay, so what we found is that f of H1 is GH1, that is G inverse H1, sorry, G inverse Y, and that is Y. So what happened is, for every Y in this coset, we have found an element in the subgroup that is carried over to this element, right? So this will mean F is onto. Okay, so what we have is that we can see that number of elements in H, okay, is equal to number of elements in GH, and as a notation we will express it by this. All right, so this is what we saw, that any two left cosets who have the same number of elements, and these left cosets are the equivalence classes, so they are going to be disjoint. So disjoint means what? I can just divide this whole group into, or I can split it into copies of this subgroup H, all right? And those disjoint copies will cover the entire group. And since they are all disjoint, what I mean is, so that is, since they are all disjoint again, the number of elements in their union, the union of all cosets, which will be G, will be the sum of the elements of those cosets that cover G. By the way, here, see, I have incomplete typing. That is what we have meant is, let me write it again here, that the number of element in H or the size of H is the same as the size of GH. Okay, and so as I said, that we can, I mean, we knew that already, that we can cover the entire set, you know, by subsets that are equal to the, that are equal in size to H. And now I'm not writing H in the other ones, but because they are not necessarily equal to H. So repeating it in this manner, what we get is that as I said, we shall have the whole group G covered by these left cosets. Okay, so what you have is that we remember, we assume that the number of elements in G is n, and say the number of elements in H is, say, m. So here I have m elements in each copy. There are m elements and they are all disjoint. Okay, so if I have, so if I have, say, R disjoint left cosets, then what will happen? R times M will be N. Why? Because the cosets are disjoint. And let me just, kind of remove just a visual anomaly. That is, here we mean following, that I have, subsets covering like this. Otherwise, it was going to be, an integer, which was just going to look, a little awkward. So what we just found is this, that if G has, so I'm erasing this now, if number of elements in, just repeating the same thing, if number of elements in G is n and H is a subgroup and the number of elements in H is m, then m divides n. Okay, or we have a positive integer r such that what? That m times r equals n, and this r we will call it index of H and G, but let's just go over that later. So what we just did was that we just proved a theorem that's called Lagrange's theorem. So what we just did was that we just proved this theorem, that if G is a finite group of order n and H is a subgroup of order m, then m divides n, or in other words, m is a factor of n. So for example, say we take the subgroup, or rather the group of z modulo 10, okay, with this as our operation, binary operation, then it cannot have a subgroup of order 3. Okay, so can not have a subgroup of order 3. Now in this case, that is for this particular group, if you take any factor of 10, that is, you take 2 or 5, you will have subgroups of those order. But the converse of this theorem, that is Lagrange's theorem, may not always necessarily be true. Okay, so what we are going to discuss is the converse of the Lagrange's theorem. Okay, may not work, okay, in this sense, and rather it will not work for all the factors of every group, okay? And what I'm going to do is that to show you an example, I'm just going to take you to the most popular example. That is, if we take A4, okay, and who is A4? A4 is the group of even permutations, okay, on 4 elements, okay? So that is if we take permutations on 4 symbols. For instance, I'm taking these permutations here, and let's see which are even and which are odd, and I'm recalling a procedure that we did in the last presentation. So how do we write these? We do this. Actually, yes, let's just, oh, sorry about that. Okay, or let me just do this here. That is, again, just fill this up. So the way I will start this is this, that I'll start with 1. Now 1 goes to 3, right? Then I'm going to 3, okay? That's the way we wrote that as a product of cycles, and then 3 goes to 1. So this cycle is actually done here, right? So we got this, and then we can write the other portion as, and what we all that we are doing is actually we are writing it as a product of disjoint cycles. So in the other one, what I did was, 2 goes to 4 and 4 goes to 2. So let me just decrease the fonts a little bit. So the way you write these is, if you remember from last presentation, okay, all right. So the way we write this is that once we are writing this as this is a cyclic permutation. That means 1 goes to 3, 3 goes to 1, and for the next one we have 2 goes to 4, 4 goes to 2. So what we have done is we wrote this permutation as a product of 2 transpositions. So number of transpositions, and the factor is 2. So this is even, right? So this is in A4. So this permutation is in A4. Now let's look at this one here. Okay, so for that one, let me quickly write the whole thing. Okay, so we have 1 going to 3, then 3 goes to 4, 4 goes to 1, 2 stays as it is. So we just ignored that, right? And then here our situation is different. That is, we have a cycle and the length of the cycle is 3. And again, what we can do is this time we can again write this as a product of transpositions. That is permutations, sorry, cycles of length how much? Length 2. And we can do this, we multiply from the right. So we got this first, 1, 4, and then we have 1, 3. So again, we have 2 transpositions in this complete factorization here. So this permutation is also even, or it is in A4. And while if we come to this one you can see 1 goes to 4, 4 goes to 1. So I can write it as 1, 4, and 2 and 3, they stay where they are. So here I have only one transposition. Transposition again is a cycle of length 2. So only one transposition. So 1 is an odd number. So this is an odd permutation. Now let's go ahead and have Sage list all the permutations of A4, and our objective is this, and I'm just saying it because uh, I have known this statement ever since I took this course myself, that A4 has 12 elements. Why? Because S4 has 24 and half the permutations are even and half are odd. So A4 has 12 elements, but we are going to see it does not have a subgroup of order 6. Okay, all right, and we are going to see that we are not going to just display all possible subsets or prospective subsets that could be a subgroup and showing that they can't be. We will be done with a shorter route. All right, so first let's go ahead and list A4, and for that we will go to Sage now. Okay, now fortunately Sage has alternating group of order 4 already in there. Okay, so we can just type it in and say list A. That means it's going to list all the elements, which it did. Okay, so let's take it to our blackboard and then talk about it there, because we don't need any computerized calculation from this point. So here we have an alternating group, and the number of elements here is 12. All right, and what we are going to show is that there is no subgroup of order 6. So no subgroup of order 6 in here, sorry. Okay, so we are actually first notice this, that it has 6, not 6, rather 8 elements, which are 3 cycles. So 3 cycle means what? 8. So there are 8 elements of order 3 each, right? Okay. So in this case, what will happen is this. Let's assume the opposite. So let H be a subgroup of A4 of order 6. Say we have one. So now what will happen? Who will be, and these are the, these are 8 elements of order 3. So let A be an element of order 3, okay, in A4. So what I'm doing is that I'm assuming A is any of those 8 elements. So any of those, the property will be carried over here. Okay, so for H, let's see. So if we look at the cosets, then one is identity, and then we have, let's not go to H squared directly, we have AH, then A square H, and A cube is what? A cube is the identity permutation, right? So if I look at these 3 cosets, then each one of them have 6 elements in there. So I can't have 3 different cosets in there, right? So what will happen? I will have either this, right? Or I have AH equals A square H, or I have what? AH equals, say, H, okay? All right, or I'm sorry, A square H equals H, because AH is already covered in here. Now, what does this mean? That if, since this equals H, so AH belongs to H, which will give us AH equals, say, H1 for some H1 in H, and that will give us A equals H1 H inverse, that's in H. So this shows us that A is in H, right? Now, on the other hand, if we have this situation, then what has to happen? AH1 has to be A square H2 for some H1 and H2 in H, because the way these two are equal, so we will have, elements H1 and H2, which will give us equality of all the elements, right? Now, if we multiply by A inverse, what do we get? We get this, right? And this means A is H1 H2 inverse, and that belongs to H. So in this scenario also we have A belonging to H. Now here what happens is that we have A square H, that's a typical element in here, that has to equal an element H1 in here. So what that will give us is this, that A square not belongs to, rather A square equals H1 H inverse, that is in H. So now if A square is in H, we want to conclude that A is in H, so we will use the closure that A square times A square is in H, right? And who is A square times A square? That's A to the 4, okay, which is A cubed A. And who is A cubed? Older is 3, so A cubed is E, right? So we have A to the power 4 equals A, and that's in H. So what we are arriving at is this, that if we take any element of order 3, okay, as we did here, okay, if we take any element of order 3 in A4, then A ends up in H, right? And how many such elements are there? There are 8 such elements, and H has only 6, all right? So this cannot happen, okay? So since this cannot happen, we cannot have this statement. And what we just did was that we have proved this statement, that there is no subgroup of order 6 in A4. Okay, so let me stop this presentation here, and in the next one, just for fun, we will begin with A4 again and proceed further. Okay.